Good morning, everybody. This is way too early to be talking about Rust, but thank you all for showing up. This is a terrible topic. This is an absolutely horrendous topic, and there's a lot to cover, so we'll try to be relatively succinct and hope that we can get a lot out of it. So first and foremost, my name is Juan Andrés Herrero Saade, which is why JAGS works for everybody. I run research over at SentinelOne and do a bit of academic stuff over at the Alperovich Institute. And this is the brains of the operation. Do you want to introduce yourself, or is that too much?
My name is Nicole Fishbin. I'm a security researcher at Intezer, and that's my first Black at USA, so I'm excited.
Woo!
Let's do Rust.
Let's do Rust. All right. The clicker is not working too well with us. So nobody should be excited about Rust in particular. I know developers are, reverse engineers are not, probably should not be. The way this all kind of comes about is actually Nicole was working on an APT that she discovered called Wildcard, and ton of interesting operations in the Middle East, and they suddenly switched over to using Rust. They had a component called Rustdown that we tried to work on together and realized that reverse engineering this stuff was, I'm not going to say impossible, but definitely an unmitigated disaster. So bringing a bit of sort of the perspective into it, it used to be hard to reverse C++ and Delphi and like all these weird edge cases. And it hasn't gotten necessarily easier, but I think in large part it was because we were going about it the wrong way. I don't know if any of you have been around for a while sort of in the reversing space. There was always this sort of like implicit, I don't know, toxic reversing culture around the notion that if you're a badass, you're reversing everything through the disassembly window, and decompilers or F5 reversing was a sort of derogatory thing that, rich noobs could do, right? That's a lovely way of thinking about things, except when you have multiple layers of abstraction. And that's what happens as we get into programs like, into programming languages like C++ and all the new paradigms. You are living in a world of abstractions that just don't make it down to the disassembly window at all. So that's what decompilers are for. And originally, we'd pay a lot of money for decompilers. Now people, have Ghidra and Binja, and it's even accessible to the masses. So we really don't have much of an excuse not to use them, other than weird hubris. And the truth is that we need them now more than ever. God, every click is 2 clicks. All right, I might just switch over here. Anyways, so things have been going from bad to worse in a way. Like, it seems like every 2 months there's some new programming language or some newfangled like memory collector, some kind of garbage collector, memory allocations. They decide they're going to do references in the stack differently. They're going to do memory boundaries differently. And that's all wonderful for devs, but it really just sucks for us. For the most part, we're talking about huge binaries. There's lots of statically linked code, all kinds of weird binary structures, unconventional or custom calling conventions. So anything to do with like arguments or whatever is usually a mess. And they have these really active development communities, which sounds wonderful, except it's not for us, because it means that every 2 months they decide to arbitrarily change some structure that we were depending on, and no one's sending out an email about it. It just happens. It may also just be that our tools also suck even more. There's a lot of limitations to existing reverse engineering tools, whether it's stuff with type reconstruction or complex function prototypes. It's very hard to model custom calling conventions properly. We can't consistently trace how arguments are being modified in some cases, specifically if they're being referenced to the stack in sort of weird scope breaking ways that we're going to discuss. You also have this really neat idea of having like multiple return values. None of the decompilers are not ready for any of that stuff. That was not something that we would deal with before. And then, we have a hard time recognizing statically linked code, recovering structures, classes, methods. All that stuff is just beyond the pale. We can barely get structs made half of the time. That's not necessarily true quite so much anymore, but it's hard still, and everything feels broken. The real issue is when nobody is looking, what you get is a thriving malware ecosystem. This is what happened with Go. You basically had an explosion of APTs and different types of ransomware and malware using Go, developed in Go, and that we had a miserable time trying to reverse because of the way that Go works and its incompatibility with our stuff. But the truth is that there's hope. And this is sort of like the key insight that kind of drives us here, which is we tried this with Go and had surprisingly good results. So why did reversing Go suck in the first place? Well, I talked about not being able to handle multiple return values. We had a really hard time with complex types and type recovery, tons of statically linked functions, right? You would compile hello world, it would be 5 megabytes by itself. And that's without, all the wonderful stuff that comes along for a 15 megabyte binary that's statically linked with everything that, that library ever included. So it was actually impossible to find like the user generated code. It was just lost in these thousands and tens of thousands of functions that had nothing to do with this. Stripping binaries obviously seemed to lose important information. We had issues where, at least in IDA Pro, where the stack would get reinterpreted all the time, and it actually, if you ever tried to reverse Go and you went to press F5 and it told you that it couldn't because there was an issue with the stack, it keeps reanalyzing this more stack context function, and since the arguments change, the stack breaks every single time unless you go and manually define the function prototype. Obviously, not ideal. And if you try to decompile the entire binary, which takes a little bit of trickery in IDA Pro, the whole thing would crash. So, fun. The solution I came up with, and I'll go through this very quickly because this is work that we've already done, it's already public, but we created this thing called AlphaGolang. It was presented at Recon originally a couple of years back, and it tried to tackle two different problems, and you're going to see the same theme in this talk as well. One of them is the brittleness of IDA Python scripts. The other one is the need to, have clear steps to analyzing these binaries, putting information back in place, and so on. And the idea was we wanted to tackle it as a sort of methodology of sorts and say, what steps should I be following before I'm even just trying to dive into the particulars of the code? The key thing for the brittleness was to have standalone scripts. I don't know how many of you have tried using somebody's amazing IDA Python tool, script, plugin, whatever that they wrote 6 months ago and it's already broken, it already doesn't work. When it's one giant monolithic plugin, it means you might as well just throw the tool away. So in order to avoid that, we opted for small standalone scripts that could be used as steps. You could choose which ones you need to use in succession, and God forbid one of them breaks, you can fix it, or you can just move on to the next steps and not have your entire project busted, right? This is just living with the realities of IDA Pro rather than this sort of idealized sense of what it should be. So really quickly, you'll find this on GitHub. We put out a YARA rule in order to identify Go binaries. Super, super simple. Nothing crazy. But then, we figured out ways to recreate the PCLN tab section, which is sort of like where all the symbols and information about the functions, the names, original names, et cetera, were stored. And that's quote unquote removed when it's stripped, but it's not. You could actually just go in and grab that again, recreate it. It also meant we could discover all missing functions and restore the function names, not some, all of them, which is phenomenal. It also meant we could surface user-generated functions. When you know the perfect structure of how the code was laid out by the developer, you can actually say, oh, there's 45,000 functions and they only wrote 12 of them. I'm going to spend my time on those 12 functions, right? We're able to fix string references. Honestly, the code on this one kind of sucks. We could probably use a little bit of help. It's my fault. Yeah, we could do it better, but we can fix string references in a way that's meaningful for IDA. And then we had people start to contribute scripts, which is great. We were able to sort of start recovering type information from the information that's left in Go. So the result was, when you looked at something like this, which is a Russian wiper that was hitting Ukraine early on in the invasion, we could take this Desert Blade wiper sample, and within a minute of just applying a bunch of scripts, we'd go from 2,400 unidentified functions to 8 user-generated functions and everything else labeled properly. And frankly, to me, that feels easier than reversing most C, C++ stuff these days. So there is a way to turn the problem around if we figure out how to use the information that's being left there. Okay, we came to talk about Rust. So with that, I'll bow out and let someone smarter than me take over.
All right, so Rust. Rust is an open source. It was officially, the stable version was released in 2015. And actually, the first report about a malware written in Rust is from 2016, and it's a Linux backdoor. But what is Rust? So we know it's a cross-compiling language like Go, and it has a very strict compiler, which enforces memory safety with some ownership systems and borrow checker. No garbage collector. It is able to grab lots of compilation errors before compiling and before running. So very strict, very hard to actually compile something. Supposed to be faster than C. It is very powerful cargo dependency manager. And it has a very strong community which releases new versions. Not every month. There is also a new version every night. So that's fun. And because it's such a strong and versatile language, we see why developers would like to use Rust. Also, we see why malware developers want to use Rust, also because it's really hard to reverse engineer. But basically, we see malware in APTs, ransomware, e-crimes. We see Rust everywhere. And we mentioned wildcard. There is also Rust Bucket, which is a sophisticated malware targeting macOS. And lots of ransomware also switched to Rust. Some malware even switched from Golang to Rust, maybe because they want to evade detection and make our life much harder. So why is it hard to reverse Rust? First of all, the binaries are huge. Even the ones that are without the debug symbols, they're still very big. And we have lots of strings, but none of them are really interesting. And I think from what we saw, most of the strings that are interesting are encrypted. Then we have huge functions with lots of stack variables. And calling conventions, they exist. But Rust supports all of them. And then the developers can decide for each function which calling convention to use, which makes reversing even harder. So we're not really touching, until now, the reversing of Rust because it's hard. Because what worked for Go doesn't work in Rust, because our tools suck, and because the reasons we're not talking about Neem or Kotlin or any other language, it is hard and annoying. So to be honest, there is no hope. Thank you. Okay, we will not give up just yet. So we want to create a project to start somewhere and to improve, to build on something and to make scripts for sure, not plugins. And our main focus is IDA Pro, though we are kind of looking into Binary Ninja and like other platforms. So that's something to keep in mind. Our process basically went from, okay, let's take some malware samples and see how they look under the hood. And also, let's compile some Rust code and see how like very simple like strings looks under the hood. So it is hard to compile Rust. It is hard to write Rust. We thought with IDA Python a lot. And we wanted to give up a few times, and we wanted to become farmers. Looks much easier life, but we're still here. And just a disclaimer. Through this presentation, we're going to talk about IDA Python and how much it was painful to write scripts and to do some stuff, but we really love IDA, and the excellent people at X-Rays are willing to help, and we're working with them to fix some of the pain points. So we love IDA, and we love Binary Ninja too.
It's a toxic relationship with IDA.
So where do we start? First, we're making a YARA rule to identify Rust binaries, similar to what we did with Go. And then we want to see what information that we can read and what we can grab out of there. So I mentioned that we have lots of strings. And when we look into them, we can see some rust-C, which is the Rust compiler, followed by something that looks like a commit version, which it is. So we can grab the actual compiler version, which is very powerful given that there are so many versions of Rust. Then, when we continue looking into the strings, we can see the cargo, which is the dependency manager, and we can see the full path. So we're going to use the full path later in this presentation, but right now what we grabbed is the dependencies. So while we're not able to maybe identify user code and library code, at least we know which libraries are used, and their versions too. Now we want to create some structures and understand the Rust structures. There are lots of them. Let's start with strings. We have strings and we have slices in Rust. So for strings, we have the capacity, pointer to the content of the string, and then the length, because you can change the capacity of strings. Slices are constants, so we have only length and a pointer to the content of the string. So we created structures in IDA, which was also painful, but we created structures for slices and strings, both for 64 and 32-bit. So now if we want to compile some simple Rust code to see how these slices and strings look like under the hood, this is an example of the source code, and here we can see the decompilation, which is not pretty, but we can understand what's going on. And we see that the content of the slice is actually stored in the our data section. And we can see that our data actually follows the structure of slices. So we have the pointer to the string itself and the length. Strings. So seems like a normal, nice string, but in the decompilation, it looks horrible. And then if we want to maybe use a mutable string, which is a thing in Rust, it looks even worse because now we have some memory operations. And if we're grabbing a string that is longer than 16 characters, we're using XMM words. And in some cases, the strings are in reverse. So it's a whole mess. So remember the structures that we defined before, and that we want to create scripts to help our life make our life easier. After running the scripts, it looks much nicer, right? It looks like code. So the issues that we're tackling here is basically that the content of the slices is in another section, and things are messed up and reversed. So we're using scripts to make it cleaner, make it nicer, and more readable. When we're looking into huge functions, this part that is all of a sudden very clear makes the life easier, even if it's a small part. Next thing that we wanted to tackle is actually the calling conventions. So I took this from the Rust repository, and this is the list of all the supported Rust calling conventions. So it's a mess. So we started to look for places which we can use to maybe understand how the stack of the calling of function calls look like. So we went into the Unwinding Info, which is part of the exception handling. So when we run a program and we hit an exception in runtime, the runtime will go over the stack, try to find the right exception handler. If it doesn't find one, the function will terminate. So to know how exactly unpack this stack, the runtime will use the unwind info. And funny thing is that we noticed that IDA didn't parse the structure correctly. The full documentation is actually a really good document by Microsoft. So we developed our own structure, and we added to IDA as well. So now our scripts goes over all the functions, and most of the functions do have this structure, and we parse the structure for each function. So we know which non-volatile registers were used and what's the size of the frame. And unfortunately, right now, it's not enough to actually define the calling convention because we need more information about the types. So that's something that we will need to fix in the decompilation. And we're looking into other formats of Dwarf for Linux and Mac.
All right, so as we kept trying to make the most of the data that we had available to us, and that's really the name of the game here. Like, I think a lot of the former programming language developers had a tendency to want to just remove data and get it out of the final binary, and I think that's where the concept of stripping was really supposed to come in as well. A lot of the newer programming language developers just seem to think that it's okay, like, to keep shoving the data into the binary, and then you can remove references, right? Like, you'll remove some pointers or a given structure, but the data stays there, and that's where we want to play and where we can do a lot of our magic. So one thing we kept seeing was these, like, calls to a function and an offset somewhere. And if you've ever played with sort of like the offsets or anything with strings in Rust, you'll notice that there's tons of indirect references, right? There's an offset that points to a place that has some data that points to a place that has the content of the string. And that's a lot of the stuff that we've had to restructure. That actually includes information that we're trying to collect and that we've put into our scripts. But in this case, we keep seeing these weird sort of offset strings. And when we look at it, you look at it, it's like, okay, there's another structure here, which I called the debug info structure. And sort of we define 32 and 64-bit versions. And when we apply it, the result you get is actually really interesting. It turns out that because Rust is so heavily macro-based, there's a lot of things that happen under the hood that developers are not aware of. So one of the things that happens when you use one of these, just the println macro, is it actually includes panic information for when it needs to unroll the stack if something goes wrong. And that panic information literally includes the file path where this is coming from, the line and column number of where the error occurred, and that ends up in the final binary. So once we had parsed it properly, we could actually bring it back into the decompilation, and we started to notice there's something really interesting because you can start to map out the standard library source code and where it intersects with what's being used in the user code. So this is one way where we started to really sort of get some really interesting information back. And then if you, again, we see what's there, we try to figure out what the info stands for, we give it structure, and we keep surfacing it to the user. The idea, again, being we're going to try to run as much of this information, giving it structure, bringing it back, so that by the time the analyst gets to the picture, all this stuff is already there. That's not the stuff that you should be trying to process in that moment. So another thing to do at that point is if you now have structured this debug info, you can start going backwards into all the references to those offsets, and you figure out, actually, here's all of the exception handling that Rust is structured for you. And we can start to identify entire portions of code that have no function labels and whatnot, but that in this case are being pointed down all the way to standard library source code. So that's one way. It's not a good way, it's not an easy way, but that is one way that we can start to kind of feel our way in the dark to what standard library code we're dealing with in some cases. We have found some better ways, objection, you know, whatever. But that's one of the ways we do it. Then came what I'll call our previous obsession, but one obsession that in particular has cost me a lot of heartache, which is there's an issue with tons of byref stack variables showing up. How many of you are familiar with what byref? Got a couple of folks. All right. So basically what it means is if you're looking at the code and in the decompilation in hexarrays, IDA will tell you if it has a variable that's overlapping another variable, so it's like way too big, or it has a variable that's being referred to sort of by reference to a specific portion of the stack. What's interesting is we're seeing tons of these byrefs, and what it's pointing to is the fact that it seems Rust does not, I'm not going to say it doesn't respect, it has a different idea of what scope should be for certain functions. And this is where you start to see why this is actually so hard and what's actually wrong. It's not handling scope the way we're used to. You say, this is a function, this is a variable within that function, it only lives within that function. When we're done, and we bail, right? That's always been the idea. Not in whatever it is that we're looking at here. What you see is functions being able to point to something in the stack that is not in their stack and making changes to that data, which is why we're not seeing the sort of data flow clearly across these different functions. We talked to some much smarter people at Recon, and Sergey Bradis and Ilfak were actually very kind about sort of starting to discuss whether this is a concept of an application of the use of closures. I don't know at that point, but the other possibility is simply that we're dealing with such bad variables, like varying stack sizes, that they're running over each other. But I don't think that's the case. In any case, I had to stop going down this path of madness because our decompilation is so bad right now that we can't fix all of the type problems and size problems yet. There is so much dead store elimination that needs to happen, reuse of variables that's currently happening that's inaccurate. And like Nicole mentioned, we're getting a lot of help from the folks at Hexrays. We hope to kind of keep improving on this. We hope that the underlying, decompiler will improve, and then we can tackle this one again. But I really wanted to point to it because I think there might be some serious answers when we can deal with this. The other thing that we could do right now, if folks are looking for a way to contribute to this, I would suggest going back to these exact examples in Binary Ninja, or God forbid Ghidra, and just seeing what's happening in those stack calculations. So maybe we can contrast and compare, see if it's a ghost in our decompiler, or if it's actually a problem that's coming down from Rust, but it's happening consistently. We count on Ilfak on this one. So beyond that, what are we working on right now? And this is like a 6-month project for us. We're not coming to you with a lot of answers. We're coming to you with like the bleeding edge of what we can accomplish as the tools continue to improve. There's something I think a lot more promising for the time being, and I'll let Nicole take that one since it's her work.
So we wanted to see if we can do something around these dependencies, sort of like library code. And maybe if we can't identify it through IDA, maybe we can identify it through other ways. So first of all, we wanted to do sort of like a static compilation for these dependencies, which is apparently also not straightforward in Rust like anything else. So we had to basically pull the dependencies using the script that we showed you before and compile it as a crate, and then use cargo tree to list all the dependencies. And then for each one of them, we would go and create basically like a simple program. And sorry, this is how the tree looks like for one dependency. That's great.
I don't know if you folks can see the code in the back, but if you go back to it, just so we'll look at a sample and you'll end up seeing like rand cha-cha, and you know the exact version of rand cha-cha, but for us to be able to identify the code, you got to walk that tree of what looks like about a dozen dependencies, and then pull each one of those, label each one of those, and work your way back up just to be able to get rand cha-cha into that one sample.
And that's the short version of this dependency tree. And the reason we're trying to make it as narrow and as accurate for each dependency is because of the way that we want to implement it. So for each dependency, we will create sort of like a very basic main that prints the crate version, and a very simple cargo that basically uses the dependency that we want to isolate. And the reason that we want to isolate it is because we have two approaches. So one approach is more similar to what actually Intezer, the company I'm working on, is doing, is basically identify these libraries or crates using code reuse. So if we can say this exact, what it is, bin code, this exact bin code is looks like that. And then if we get a new sample, we will be able to identify this code reuse and basically narrow down the functions and the code that we need to look for. And the other approach is actually making flirts.
So part of the reason that we wanted to compile these things is IDA's been doing a lot, Hextra's been doing a lot of work on improving the development of FLIRT signatures. There's AlphaGolang and like all this other stuff that they're introducing. And I think we're kind of halfway through to like a big rollout from Hexray, so I don't want to throw shade at them at all. I'm excited for whatever's coming. Right now, making FLIRT signatures is not like necessarily the easiest thing, but just think of, this is where like the academic in me wishes I had like a whiteboard, right? Think about the process and the way that it's developing right now. We get a binary, we have the easy ability to pull out what dependencies are by name and version. We can, in theory, cross-compile all of those for the different architectures and bitness and, you know, platform. In theory. I say that in theory because it's been a complete pain in the ass, but in theory you can do it, right? So we'll go, if we have to set up a VM, we'll do it. But you can compile that as a standalone exe. Then we can get IDA to analyze that headless and take a script like idb2pat, which we've modified a bit, and come up with a FLIRT pattern, and then try to make a FLIRT signature out of it. All of that would allow us to then take a .sig file, apply it to IDA, reanalyze the whole binary, and hopefully get a bunch of our functions already identified. That's what IDA should be, well, that's what IDA tries to do for you with the existing type libraries that it has. It's a very limited amount of type libraries, and there's a lot of debate here as to why we've never just created one giant library of type library files for everyone. Anyway, so I won't get into it, but that is the approach that we're considering for the time being. I would love, we thought about trying to do like a GitHub Actions type thing where it all compiles and then creates the SIG for you, but we can't shove IDA in the middle of that pipeline, at least not in the cloud. So in the meantime, I think we're at least going to start to, we have another project that we're involved in that I'll tell you about in a little bit that will hopefully give us a survey of dependencies, and we're going to try to put out as much of the really valuable ones as possible. So where does that put us for now? I know I've come to talk to you about something that sounds ultra alpha or beta, but the truth is that we need to approach it this way because this whole project is going to have to be a living project for all of us, or it's not going to work. In the sense of, we're trying to get as much of this information as possible. We're trying to make it as available to everybody. The wonderful Rustaceans out there who are enthusiastically changing the compiler and all this crap under the hood every 2 months are going to keep doing what they do. And we're going to have to keep trying to figure out how to wrestle information out of their hands. But I think the valuable thing here is to note just how much of that information is there. Up until a few months ago, the best you would get with like Rust reversing tutorials, except for Cindy Shao, who's done amazing work on the Binja side, is mostly just people trying to tell you how to figure out strings. Yeah, strings are wonderful, and we've taken care of that for you, and there's a script that will, you know, we can apply the structs, and then we can apply the right types, and you're going to see that information pop up. Great, you have strings. The other 40,000 functions that need to be identified is the stuff that we're actually concerned with, the ABI, being able to figure out the calling conventions, being able to figure out what the stack sizes should look like, being able to figure out where information is being modified. That's where the magic is, and we're chipping at it little by little, and we could use help. So we're going to put up the project .xal at GitHub this week. It will come with scripts for all of the things that we've talked about so far, recovering the panic paths, being able to place the slices and structs, being able to infer dependencies with versions, and we'll start to, then we're going to start to put up some of the dirty stuff that we haven't quite figured out completely, but that we hope we can get some help with, right? The harness to be able to compile things, to be able to create the signature files and so on. That will, I'm sorry, that will probably have to come down to a it works on my computer type situation, just because how do I set up some IDA anything for you guys in any meaningful way, but we'll do our best to make it robust. In the meantime, I wanted to point out a couple of other projects we had to develop in the process of this with varying success. So if any of you are Power IDA Pro users and you were checking your emails a few months ago, there was an announcement that they're going to change IDA Python again. So I'm sure it's for the better. IDA needs to be improved. It really is very brittle. It sucks right now. But it also means that if we're building this whole project in IDA and someone's going to come and change it, like, I was ready to, swallow a gun at that point. So instead, we made this thing we call feature proof. And it's a middleware library where we've put really obvious things you need to do with obvious names to do them as functions. And that way, we can have perfect compatibility with the current IDA API, and then we can go in and modify just that library and hopefully have our script still work after that, something we learned from the equation group's development tactics. The other thing I tried to create and gave up on and failed miserably, and if anybody can figure out how the hell to do this, I would, I'll buy you a beer or 10, is we tried to create a generalized structure creator. Right now, we have all these structs, and you can manually go in and easily put them. You'll literally go in the C syntax. You can paste 10 of them at the same time, and they pop up, and that's fine. Great. I wanted to create a thing that would just be able to introduce new structures without you having to do anything, just run an IDA script. After 49 iterations of this with my handy Gabo RE, my ChatGPT bot designed for IDA Pro stuff, which you guys are welcome to use, we gave up and realized that there's just no way to really do this consistently or well just yet, but that is a thing we're trying to get working, and we're talking to the Hexrays guys about. Where to from here? Because honestly, this is very much a call to action. Like, Nicole's brilliant. I'm okay. We can do a lot. I don't think we can tackle this whole problem by ourselves, but if we start to structure some of this stuff, I think it will be a lot easier for other folks who are much smarter, much more familiar with, let's say, Dwarf or Unwind Information for Mac, which is a completely different format, or any number of other structures, or stuff about complex types that is still hiding within these binaries. We can surface all this information and put it up to some extent. So, folks, more information about the particulars about different platforms and architectures. Like I said, we're looking at all this like structure and exception handling information for Windows. Turns out completely, as you would expect, different for Mac and for Linux. More promising in some of those languages. When you look at the information that's being left behind for Linux, it's much more comprehensive. What can we pull out of that, right? There's a lot of the stack unwinding information we're kind of obsessed with, because if we can get it right, if we can figure out more, we could fix the calling convention problem, right? If you know what the stacks are supposed to look like, if you know what the non-volatile registers are, you can start to infer what the calling convention should be. So this problem that everybody says is like, this like heart attack problem with reversing Rust is fixable. It is within reach. Obviously, we want to do more with type recovery and size mismatching of local variables. I'm sure that's hiding a lot of problems for us. We need to fix this. This is stupid decompilers, but we need to fix them, because right now, part of the reason we're not coming here and telling you, like, pulling up the Bush mission accomplished banner is when you pull this stuff up in the decompiler, there's 20 ghost variables that shouldn't be there or that should be there, be used in a different way. And then if you pay really close attention halfway through, it starts to reuse the same variables for things that are completely unrelated. So it's a disaster. There are things we can do right now, because we do have to decompile and like reverse Rust ASAP. But there's also things that will have to come with improvements from tools. And we're trying. And like I said, the Hexrace folks are being very helpful right now. Then this is a 6-month project. We're on month 2, I want to say. Basically, our plan is we're going to put our efforts into this until the end of the year and try to get as far as we can by the end of the year. And sort of bring everybody along, hopefully, and get we hope we get a vibrant community of folks. We're already getting some folks who are starting to introduce stuff here. And a part of this that I'll say is if you're not big IDA Pro users, but you're really interested in this problem, Binary Ninja is having completely different results and problems, but also really promising things that are coming up there. They have a really good support structure. They're very invested in helping folks out. if you are a Power Binja user or Power Binja plugin developer, we'd love to be able to port these same features back and forth, and then I think we're going to start to get more information that gives us some ground truth where our tools are failing versus where Rust is introducing weird stuff. Our eventual goal is actually to be able to hunt deeper into the Rust malware ecosystem. The likely outcome is that we will, again, choose to become farmers. Have we learned anything that will help us with hunting? No. Well, a little bit, maybe. The next thing that we're going to unveil on this beyond the scripts is we're actually working on a survey of all compiled Rust code as best as we can get it. Shout out to our friends at VirusTotal who are being extremely helpful with sourcing a lot of information and whatnot. This is us trying to turn to like the big data side of it. We have an AI component that's helping us. We're hoping a big data component will help us. And if not, just using those words, maybe we'll just get VC funding and pretend that it's all golden and get a vendor booth or something. Anyways, I'm hoping we have time for Q&A, but thank you all for being here and for trying to stomach this frustration. Can't spell frustration without Rust. And we hope that in the next 2 months, we'll actually have a much nicer ecosystem that we can go after, understand what's happening in these, be able to reverse them, and then I promise you the amount of malware that is going to shake out will keep us all happily employed in this trash fire forever. So, do we have time for questions? Yeah? We're out of time? All right. Find us in the wrap room. Thank you all so much. GitHub will go up. We'll tweet it. We're out.